So let's talk a little bit about the limit definition, kind of work our way up to all the things. So there's kind of two different ways of viewing the limit definition of the derivative. And I should write some Co-21A. Today is February 1st. So limit definition of the derivative. And like I was saying, there's kind of two ways of doing this. You can either think of the derivative at a point. So the derivative of f of x at the point a comma f of a is given by, and there's actually two equivalent definitions. I'm going to give you the better one in my opinion, but I'll note the other one. The limit as h approaches 0 of f of a plus h minus f of a all over h, which I'm going to write as f prime of a. I will alternatively note, just because I think it's worth noting, or you can also write it as the limit as x approaches a of f of x minus f of a all over x minus a. That is also a way of finding it. And just because it's interesting, I'll point out that you can get from this definition to this definition by letting x equal a plus h. I want y'all to think about that for a second. If x is a plus h, and a plus h gets closer and closer to a, then h has to be getting closer and closer to 0. Just like over here. And if you replace the x with a plus h and the x with a plus h, then you exactly have the same expression over here. So these are two different ways of writing the same thing. I will point out that this first way is typically computationally easier to deal with. Although we can certainly explore both of them if we care to. And then another definition, which is going to feel very much the same. The derivative of f of x as a function is given by f prime of x equal to the limit h goes to 0 of f of x plus h minus f of x all over h. It looks pretty much the same as the thing I wrote just above it. The only difference in our thought process here is that up here we're thinking of a as actually being a real number, like 1 or 5 or -2. Whereas down here we're thinking of x being the variable x. Let's look at some examples. Yeah, that's a good example, sure. So let's say we want to find the equation of the line tangent to f of x equal to the square root of 2x plus 5 at a equal to 2. So to find the equation of tangent line, you need two things. You need a point and you need a slope. My point, I'm going to get by plugging in my a value here to the function. So the point's going to be a comma f of a, which if I plug in 2 here, 4 plus 5 is 9, square root of 9 is 3. So my point's going to be the point 2 comma 3. The slope, on the other hand, we find the slope by finding the derivative. I should say, we find the slope of the tangent line by finding the derivative. So I could do this one of two ways. I'm going to do it the first way, meaning I'm going to find the slope at a equal to 2. I'm going to find f prime of 2. And that's going to be equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. If I wanted to, I could instead just use x's and then the very end plug in 2. But I'm going to do it this way just because sometimes it's worth doing it this way. So let's see what we get. This is going to be the limit as h goes to 0. When I plug in 2 plus h for x, I'm going to get the square root of 2 times 2 plus h plus 5 minus f of 2. We already know what f of 2 is. It's 3. Right, when we plugged in 2 here, we got 3 for the function, or you can plug it in again. Divided by h. So our goal for these kinds of situations, whenever you're doing limit definition of the derivative, your ultimate goal is to make the original h in the denominator go away. You want it to cancel out. To do that, we typically have to employ some algebraic methods. Here, I'm going to simplify the numerator just a little bit and write it as the square root of 4 plus 5 is 9. 2 times h is 2h, so 9 plus 2h minus 3 over h. You might notice that if I plugged in 0 for h, I would get 0 over 0, which we have some experience in dealing with limits like these. We're going to multiply the top and bottom by the conjugate, just like we did when we were doing 0 over 0 limits that had square roots. And just like we did that before, we actually multiply out the conjugates and we leave the not conjugates as separate factors. So I'm going to write this as the limit, as h goes to 0, of the denominator is just going to be h times the square root of 9 plus 2h plus 3. And the reason we're doing this is we're trying to make that h cancel out. There's no value in multiplying it through the bottom. In the numerator, I get 9 plus 2h. The middle terms cancel out. That happens every time. And then minus 3 times 3 is minus 9. You could write out the middle terms. I'll point out, right, you would get square root of 9 plus 2h times 3, and the square root of 9 plus 2h times negative 3. And if you add those together, they're the same things, but opposites, so they cancel out. Simplifying the numerator, I have the limit as h goes to 0 of 2h over the same denominator, h times the square root of 9 plus 2h plus 3. Finally, dividing h by h and getting 1. You can probably skip this next step I'm about to write and just plug in 0. I kind of like to write it all out before I plug in the 0. Limit as h goes to 0 of 2 over the square root of 9 plus 2h plus 3. Then we finally substitute in 0 for the rest of the h's, and you get 2 over the square root of 9 plus 2 times 0 plus 3, which is 2 over 6, which is 1 over 3. Doing it this way gave us the slope of the derivative, or sorry, the slope of the tangent line at one particular point. Or more generally, it gave us the derivative at one point. And then if I asked what's the derivative when a equals 3, you'd have to do all this again. And if I asked what, right, for a equals 4, I have to do all this again. So the point is that doing it this way is fine, but if you want to kind of say more about the general derivative, this is tedious. It's a lot of work to get the same information every time. To answer the question that was asked, we have our point, we have our slope. The equation of the tangent line is going to be y minus the y coordinate equal to the slope times x minus the x coordinate. You could leave it like that, or you could simplify, solve for y, you get y minus 3 equals 1/3 x minus 2/3. And you can add 3 to both sides and get 1/3 x, and negative 2/3 plus 9/3 is 7/3. But that's not really the point. The point of this problem is that we found the derivative, aka the slope of the tangent line, by using this limit definition of the derivative at a particular point. And sometimes it's necessary to do that. Sometimes it's not. Let's look at a few more examples. Let's see, what have I got here? Sure, yeah, oh, that's fun. Yeah. That's not so fun, sure. So let's say we want to find the derivative of f of x equal to x cubed minus 2x at values 1, 2, 3, and 7. I really don't want to do this 4 times. You don't either. So what we're going to do is, instead of finding the derivative at one point, right, we're not going to do this. So we're not going to find f prime of 1 equal to the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. And then do that for 2 and 3 and 7. Instead, we're going to find the derivative of our function as a function. Now, I imagine many of you already know what the derivative is. You might already know it's 3x squared minus 2. But if you're asked a question like this on your test, and they say use the limit definition, just writing down that it's 3x squared minus 2 might get you 0 points, because you have to do the thing that's being asked to be done. So to find it using the limit definition, we're going to say that the limit as h approaches 0. I should really write f prime of x over here, sorry. F prime of x, the derivative of f is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. I would always recommend writing this first step down. It at least shows the person who's reading your work that you know what the derivative definition is. No, I'm getting water everywhere. Okay, so now we're gonna write the limit as h goes to 0. We do need to write the limit like every step. F of x plus h, I'm just taking my function here, and I'm, instead of being x cubed minus 2x, I've got something cubed minus 2 times something, where the something is x plus h. Try to avoid the water there. Minus f of x. Minus x cubed minus 2x. Now be careful here. That's not right. I need parentheses, and here's why. Over here, when I distribute this minus 2, I'm going to have a minus 2x. That minus 2x needs to end up canceling out with the positive 2x I should have over here, because there should be parentheses there. The things that don't have h's in the numerator need to end up canceling out, because we want that h in the denominator to go away. Ooh, x plus h cubed. Good times. Who's heard of Pascal's triangle? Really neat. So for those of you that haven't, here it is. So Pascal's triangle, we'll come back to that, don't worry. Pascal's triangle looks like this. You start with a 1 and a 1 and a 1, and then each subsequent row, the middle terms, the terms between those two ones, you add those two ones to get 2. And here you get 1, and 1 plus 2 is 3, 3, 1, 1, 1 plus 3 is 4, 6, 4, 1, and so on. Goes on forever and ever and ever. It's a really neat triangle. There are so many cool patterns in it. If you ever take stats or probability and start talking about like the choose function or the binomial coefficient, it shows up there as well. Like how many ways can you pick a group of 3 people out of a group of 10 people? 10 choose 3. That number shows up here down in the 10th row or the 11th row, whatever you want to call it. Here's what I want you to see. X plus h to the 0th power is 1. X plus h to the 1st power is 1x plus 1h. And let's go this way just so we can give ourselves some room. X plus h squared is 1x squared plus 2xh plus 1h squared. Give myself enough room. But what I'm trying to point out here is that these numbers give you the coefficients of the terms in the expansion. And the powers, you start with x to the highest power, whatever it is, in this case squared, and then the power of x just decreases by 1, the power of h just increases by 1 every term. So x plus h cubed ends up being 1x cubed plus 3, and then we get x to the 1 less power, h to the 1 more power, plus 3 times x to the 1 less power, h to the 1 more power, plus 1 times x to the 1 less power, h to the 1 more power. Or x cubed plus 3x squared h plus 3xh squared plus h cubed. And you can keep going this way. We don't really need to, but if I asked you, what's x plus h to the 5th power, you could look at this row that has the second number being 5 and say, okay, it's going to be x to the 5th plus 5 times x to the 4th times h plus 10 times x cubed times h squared plus 10 times x squared times h cubed plus 5 times x times h to the 4th plus 1 times h to the 5th. So it's a pretty convenient way of multiplying out something raised to a positive integer power. It's also nice later on when you might need to multiply things out for whatever reason. Like later on, you might have to multiply something like, I don't know, 2x plus 3 to the 3rd. And then you're like, okay, that's the first thing, that's my second thing. So it's going to be 2x cubed plus 3 times 2x squared times 3 plus 3 times 2x times 3 squared plus 3 cubed. Kind of neat. Back to the problem at hand. X plus h cubed ends up expanding out as x cubed plus 3x squared h plus 3xh squared plus h cubed. Distribute the minus 2, you get minus 2x minus 2h. Distribute the minus sign here, you get minus x cubed plus 2x all over h. And then let's see. Hopefully all the things that don't have h's cancel. Sometimes things that do have h's also cancel, but for sure all the not h things should cancel out. The x cubed and the minus x cubed add to 0. The minus 2x and the positive 2x add to 0. Everything left has an h in it. So factor that h out. You have a 3x squared. You have a 3xh. You have an h squared. And you have a minus 2. Cancel or divide the h to get 1. And the limit as h goes to 0 of 3x squared plus 3xh plus h squared minus 2 is 3x squared plus 0 minus 2. And that is f prime of x, or the derivative of the function in general. And then to answer the question that was actually asked, we can just plug in those values. So f prime of 1 would be 3 times 1 squared minus 2, which is 1. And f prime of 2 would be 3 times 2 squared minus 2, which is 12 minus 2, which is 10. And so on and so on. F prime of 3 would be 3 times 9 minus 2. And f prime of 7, why did I pick 7? I don't know. Would be 3 times 49, which is 147 minus 2, which is 145. But again, that's not really the point. The point is that we can take the derivative of the function using this limit definition and get this nice expression. Questions so far? Okay. Let's see. Do I have anything to say about this before I move forward here? Yeah. Oh yeah. So sometimes when you might need the limit definition that I think are kind of interesting. Slash, like you might actually, I wouldn't be surprised if someone asked you a question like this on a test. So someone might ask you to prove that f of x equal to the absolute value of x over x is not differentiable. Oh, sorry, that's actually not the function. I'm sorry, not over x, just, yeah, oh, geez, oh my goodness. Sorry, let's try that again. Actually, let me finish the thought here, since there is something we're saying here. This one's easy to answer. Prove that this is not differentiable at x equal to 0. Easy. If you plug in 0, what happens? Right. F of 0 is undefined, which means the function is not continuous at 0. And continuity is a requirement for differentiability. So f of x cannot be differentiable there. But that's an important thing to know. If a function is differentiable, it had to have been continuous. The reverse is not true. If a function is continuous, like the absolute value of x, it doesn't have to be differentiable everywhere. So if I said prove that f of x equal to the absolute value of x is not differentiable at x equal to 0, that could be a little more challenging. Like it feels like it should maybe be obvious. Like, yeah, look at the function. Here's the absolute value of x. It's got a sharp corner there, which means it's not differentiable there. Or as I'd say, it's got a pointy point. It's not differentiable where the graph is pointy. The graph should be smooth for it to be differentiable. But how do you actually prove it? Well, we go back to the limit definition. So the derivative at 0 would be the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. So now our question has changed from showing something is not differentiable to showing that the limit doesn't exist. Because if this limit doesn't exist, then the derivative doesn't exist at this point. Okay, well, let's actually figure out what we've got here. F of h, well, f of h is the absolute value of h. F of 0 is the absolute value of 0. So I'm going to look at the limit as h goes to 0 of the absolute value of h over h. And this is where we have to use the piecewise definition of the absolute value of a function. You really can't do this question without that. So I'll remind everybody that the absolute value of x is equal to x if x is already bigger than 0. It's equal to the negative of x if x is less than 0. And then you can put the equal sign wherever you like. Think about the way the graph looks, right? If x is positive, the graph is y equals x. If x is negative, the graph is y equals negative x. So now we're going to look at the two-sided limit here. Let's look at the limit as h approaches 0 from the right of the absolute value of h over h. Well, if we're approaching 0 from the right, then h is positive. And the absolute value of a positive number is just that number. So the limit as h approaches 0 from the right of h over h is going to be the limit as h approaches 0 from the right of 1, which is going to be 1. Which again, looking at the graph, not surprising that the derivative is 1 as we come at 0 from the right. The slope of the line is 1 the whole time. And you might be able to see where this is going to be a problem, right? If we look at the limit from the other side, well, then we're over here, and the absolute value of h is going to be, sorry, negative h. Because if h is already negative, then the absolute value of that has to be negative h to turn it positive. Think about taking the absolute value of negative 5. It's going to be negative 5, which is positive 5. But then, sorry, that is a minus superscript there. I just screwed it up. Then negative h divided by h is negative 1, and the limit as h goes to 0 of negative 1 is negative 1. And oh, look, those don't match. Which means the limit doesn't exist, but the limit was the derivative, so that means the derivative doesn't exist. So f prime of 0 does not exist for this function. Or in other words, f of x is not differentiable at x equal to 0. Kind of funky. But this is a pretty standard way of showing that this function is not differentiable at that one point. It is differentiable everywhere else. Everywhere else is smooth. It's not pointy. But at that one point there, the function is not differentiable. I see faces that feel like there might be questions. Yeah.
Why is the denominator for of h not negative h? Because h is less than 0, so shouldn't the number also be negative?
Well, but the thing is, so again, here's the thing where you're right, h is negative. So the denominator is negative because h is negative. I know it feels like I'm saying like the same thing over and over again, but what's happening here is like, for example, let's say h was negative 5, right? So if I do the absolute value of h over h and I plug in negative 5, the top is the absolute value of negative 5. The bottom is just already negative 5. So I don't need to change the sign of the bottom because it's already negative. And then the absolute value of negative 5 is negative 5 over negative 5. The negative 5's cancel to 1, and I'm left with a negative 1 on top. Or you can say it's 5 divided by -5, which is -1. Whereas if I plugged in +5, the absolute value of +5 divided by 5 is just 5 divided by 5, which is 1. Excuse me. So yeah, sometimes things are weirdly not differentiable places. Let's look at one more example of that. So here's another kind of typical example. Let me pick the right one here. Yeah. Is that the one I really want? I just want to make sure I'm not doing the terrible thing. Yeah, we can do that. Is f of x equal to x minus 1 to the 2/3 power differentiable at x equal to 1? This one's actually, sorry, can you see that? I can't see if you, I should be able, I can look right here. Be smart. So this one's actually not nearly as terrible. It's terrible to find the derivative everywhere, but it's not terrible to see if it's differentiable at 1. So we're asking the question, what's f prime of 1? Well, limit definition. So limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. So let's see here. Actually figuring out what we've got. F of 1 plus h is going to be 1 plus h minus 1 to the 2/3 power. But 1 plus h minus 1 is just h. That's h to the 2/3. Minus f of 1, which is 1 minus 1, which is 0 to the 2/3 is still 0. So really, I've got the limit as h goes to 0 of h to the 2/3 over h. And if I plugged in now, I'd have 0 over 0. So I can't do that. I have to do some algebra. I can simplify this. H to the 2/3 divided by h to the first is h to the 2/3 minus 1 is -1/3. Now here's where you need to be extra careful. You might convince yourself incorrectly that you can plug in 0 and 0 to any power is 0. It's not a true statement. 0 to any positive power is 0. But 0 to a negative power is like having 1 over 0 to that same positive power. And then 0 to a positive power is 0, and 1 divided by 0 is undefined. Does not exist. So this derivative does not exist. F prime of 1 does not exist. So f of x equal to x minus 1 to the 2/3 power is not differentiable at x equal to 1. Graphically, we can see why. I like to call this the bird function because it kind of looks like the bird a not very artistic child or adult might draw. Kind of looks like this. Maybe like those birds like that. The bird function. But it's definitely pointy right there. We have a cusp there. And just like when you have a corner, when you have a cusp, that typically means the function is not differentiable. The derivative does not exist there. Because the slope of the tangent line is undefined. Okay, I feel like we said enough about that. So differentiability can be interesting. Yeah. Let's move along. Let's start talking about the power rule. Everyone's favorite rule. Problem. It's the easiest rule to know. And actually, we're going to use Pascal's triangle. So let's think about finding some derivatives of some things. So let's start off easy. Let's say our function is f of x equal to 1. I keep looking up there to try and see things. I should just look down here. I should really just move you down. Yeah, that's better. Okay. That's the problem, is I keep trying to, there we go. Much better. Okay. So let's graph it. So here's f of x equal to 1. What's the slope of that line? 0. Y equals X minus slope 1. But if you think about it, the slope is the rise over the run. And if I go from any point to any point, how much rise do I get? None, right? We're at the same elevation. So I've got 0 rise over a non-zero amount of run, and 0 divided by not 0 is 0. We could also use the limit definition, although it feels kind of funky here. If I want to find f prime of x as the limit as h goes to 0 of f of x plus h minus f of x. Oh, this is actually an important point, so I'm glad we're doing it. So if I plug in x plus h, what's f of x plus h going to be? Nobody wants to say it? F of x plus h is 1. There's nothing else it gets to be, right? Any input, whether you're plugging in x plus h, or x, or 5, or 7, or a billion, you get 1. Minus f of x is also 1. Now here's an important piece of information that sometimes people overlook. When you're doing this limit, you're letting h go to 0, but only after you have done everything else. 1 minus 1 is 0. And importantly, when we talk about limits, h is getting really, 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 really close to 0, but is not equal to 0. So this is 0 divided by a very small number that is not 0. The 0 divided by any non-zero number is just 0. So you have the limit as h goes to 0 of 0, and then the limit of any constant is that constant. So we get 0, like we expected we would, right? We already thought the derivative was going to be 0. Now we've just proved it. We'll do a few more. Let's look at f of x equal to x. And now the slope will be 1. Means our derivative will be 1. So let's do the same thing. F prime of x is going to be the limit as h goes to 0 of f of x plus h minus f of x over h. This one's pretty nice. F of x plus h is just x plus h. F of x is just x. X minus x is 0. The limit as h goes to 0 of h divided by h. Well, h divided by h is 1. And then the limit as h goes to 0 of 1 is just 1. So great, the derivative is what we expected it to be, a constant, 1. And now things start to get more interesting. What if we do f of x equal to x squared? Right, it's going to be 2x. But it's nice to be able to show it, because again, have you had your first exam yet? No. I can't imagine that on one of your exams you will not be asked to use the limit definition of the derivative to prove some derivative is equal to what it's equal to. So it's good to practice it. So here, if I want to find f prime of x, limit as h goes to 0, right? It's the same definition every time. It gets a little old, but it's all right. Limit as h goes to 0 of f of x plus h minus f of x over h. And then that's going to be the limit as h goes to 0 of x plus h squared minus x squared all over h. And be careful here. We do have to be careful is the only word I can think of, really. We have to be careful when we multiply things out. X plus h squared is x squared plus 2xh plus h squared minus x squared all over h. The non-h things cancel. You could either think of factoring out an h from the rest of the terms or just dividing each thing by h. 2xh divided by h is 2x. H squared divided by h is just h. We let the remaining h's go to 0 and we get 2x. As everyone expected. Or as everyone who was expecting something to happen expected. Let's do 2 more. And then we'll talk big picture. Let's say we have f of x equal to x cubed. So when we do this, I want to point out that when I find f prime of x, which is the limit as h goes to 0 of f of x plus h minus f of x all over h, look what happens. we get the limit as h goes to 0 of x plus h cubed minus x cubed all over h. And when we multiply out x plus h cubed, there's three things I want you to observe. The first term is going to be x to that power, which is going to end up canceling out with the x to that power over there. The next term is the power times x to the 1 less power times h to the 1 more power. And the rest of the terms have higher powers of h. So I have 3xh squared and h cubed. So the x cubes cancel. And then when I divide everything by h, everything that has a power of h that's higher than 1 is still going to have an h in it after I do the division. So I'm going to get the limit as h goes to 0 of 3x squared plus 3xh to the first plus h squared. And then all the terms that still have an h in them are going to end up being 0 because we plug in 0 for h and we get 3x squared. And that kind of pattern persists. So if we want to find, we'll do one more. I feel like, sure. Keep going back and forth. Sorry, very indecisive. Let's look at x to the 4th. We already know what the answer is going to be. The derivative is going to be what? 4x to the 3rd. Make sure people sometimes tend to forget the power part because they get so used to thinking of x squared being 2x. When you think of the derivative of x squared, I would really like you to say the 1 in your head. Say the derivative of x squared is 2x to the 1st. To remind yourselves that the new power is 1 less than the old power. So here, we find the derivative, real quick it's going to be the limit as h goes to 0 of, I'm going to skip writing the definition part and just go to x plus h to the 4th minus x to the 4th all over h. This is where the Pascal's triangle is paying off. We're going to see this is the limit as h goes to 0. X plus h to the 4th is x to the 4th plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the 4th minus x to the 4th all over h. The x to the 4th cancel. Everything else has an h in it. The first term, you lose the h when you divide by h. The rest of the terms still have an h or more. And so they all end up going to 0 when we take the limit. That's not so the part of the definition is that it is the limit as h approaches 0. So for any definition of the derivative question, the definition of the derivative is always going to be that f prime of x is equal to this limit. And I know we talked about this a little bit last time, but again, the idea really is that for that kind of thing, what's happening is you've got some function and you're trying to find maybe the derivative, say like right here. And so what we're doing is we're saying, okay, well, there's x plus h over there. We're finding, I want to find, I can draw it okay here. I want to find the slope of the tangent line. So the slope of the tangent line is equal to the derivative. And the way we talk about finding that is by finding the slope of secant lines and then letting those secant lines get to be closer and closer to the actual tangent line. So there's my secant line. And the slope of that secant line is, well, this point here is x plus h comma f of x plus h. This point here is x comma f of x. And the slope of that secant line is the difference in the y's. Exactly. But that's just f of x plus h minus f of x all over h. And then, and here's the important part, if we let this point get closer and closer to that point, so the secant line gets closer and closer to being the tangent line, well, then we're letting the distance between these 2 points, which is x plus h minus x, we let that distance get smaller and smaller and smaller. In other words, we take the limit as that distance h goes to 0. And that ends up being the slope of the tangent line. AKA the derivative.
As the limit as h goes to 0.
Uh-huh.
Okay, so even like both of them shifts.
I mean, this one stays right here, and this point moves over here, right? Like maybe it's here. So then like you're doing that secant line, and then we move it further, and then we're doing that secant line, and we move it closer and closer and closer, so that the distance between those 2 points, the distance h between those 2 points gets smaller and smaller and smaller and smaller and smaller. So we're always taking the limit as h approaches 0 of this difference quotient. And that is how we typically define the derivative. Also, if h weren't going to 0, it'd be easy. Then you just plug in whatever h was and say it's this number, because there wouldn't be a 0/0 issue. So now let's actually do the power rule, which I imagine some of you have seen in class already. That's fine. So let's say we have f of x equal to x to some power. And we are going to make the assumption, even though this rule is true for any number p, we're going to assume for right now that p is a positive integer for right now. And the reason we need to do that is so we can use Pascal's triangle. So x plus h to the pth power, we're just gonna say, well, it's gonna be x to the p plus. So I want to point out one thing you might have observed from Pascal's triangle. I hid it for myself over here, sorry. Somewhere in this pile of papers here. Maybe. Yeah, there we go. So I want to point out that in Pascal's triangle, the second entry is always the power you're working with, right? X plus h cubed, the second entry is 3. X plus h to the 4th, the second entry is 4. X plus h to the 5th, the second entry is 5. It's always going to be the case, because, right, that you're always just getting one more in that entry every time you go down one row. I typically call this first row the 0th row. And this is the first row, second row, third row, fourth row, fifth row. So every row, the second row entry is the number of the row. So if we're going down to the pth row, the second, right, if we go down, like we've got 1, p, other numbers, p1, the second coefficient is going to be p. So that we have x to the p plus p times x to the 1 less power, h to the 1 more power. And then we have other coefficients that I don't really care about. We could find them if we really, really wanted to, but it's not that important. Some people like to tell you that this next one is like p times p minus 1 over 2 times x to the p minus 2 times h squared. But it doesn't really matter. What I care is that I have something, some coefficient times x to the p minus 3 times h to the 3rd, all the way down to the last couple terms. I am going to get p times x times h to the p minus 1 plus 1 times h to the p. Because there is symmetry, right? The coefficients always have this, are the same at the end as they are at the beginning. And then if I want to find the derivative here, check it out. It's going to be the limit as h goes to 0 of x plus h to the p minus x to the p all over h. But we can see that if you do x plus h to the p and you subtract off x to the p, let's just write it out. The limit as h goes to 0 of x to the p plus p times x to the p minus 1 times h plus number we don't care about times x to the p minus 2 times h squared plus other number we don't know, x to the p minus 3 times h cubed plus all the way down to p times x times h to the p minus 1 plus h to the p minus x to the p, all over h. X to the p minus x to the p is 0. Everything else has an h in it. And just like before, every term after this term has a power of h that's higher than 1. So when we divide out an h, all these terms here are going to be left with h to some positive power. So we're going to get the limit as h goes to 0 of p times x to the p minus 1 plus p times p minus 1 over 2 times x to the p minus 2 times h plus c3 times x to the p minus 3 times h squared plus all the way down to p times x times h to the p minus 2 plus h to the p minus 1. And if we let h go to 0, all of these parts go to 0. So we are left with, not surprisingly, p times x to the p minus 1. That's the power rule. So the power rule says that if f of x is equal to x to some power, then f prime of x is equal to that power times x to the 1 less power. Or more succinctly written, in my opinion, the derivative of x to the p is p times x to the p minus 1. And this is true for any real number p. P could be positive, p could be negative, p could be a fraction, p could be irrational, it could be any real number. P could even be 1 or 0. Totally fine. It is kind of funky when p is 1 or 0, though. Let me just point out, right? If f of x is equal to x to the 0th power, then f prime of x is equal to 0 times x to the negative first. So that's a really weird way of saying that if f of x equals 1, then f prime of x equals 0. Because that's what we've actually said. X to the 0th power is 1, and 0 times whatever is 0. So don't use the power rule when you have x to the 0th power. Just remember that the derivative of a constant is going to be 0. Whether it's 1 or whether it's 7, right? You still don't have an x, so it's going to be 0. Let's see. What else to say here? Lots of things. That time. Sure. So then we kind of just start throwing the power rule at everything. For example, if you have f of x equal to x to the 10th plus 1 over x cubed plus the fifth root of the square, the fifth root of x squared, I want to find f prime of x. And as you will see a lot, it is almost always beneficial to simplify your expression before you start differentiating. Yeah, if you knew the quotient rule and the chain rule, you could use those to find this, but you shouldn't. You should instead simplify first. Rewrite f of x as x to the 10th plus x to the negative third plus x to the 2/5 power, and then use the power rule. F prime of x is going to be 10 times x to the 9th minus 3 times x to the negative 3 minus 1 is negative 4. And then plus 2/5 x to the 2/5 minus 5/5 is negative 3/5. And that's how I would figure this out. Why don't you all try the following? For f of x equal to 5x to the 7th plus 6x to the 1/2 plus 8, find f prime of x. So let's see, for this first term here, the 7 comes down, and 5 times 7 is x to the 6th. 6 times 1/2 is x to the, and the derivative of 8 is, right. And you all just used two rules that you didn't even have to think about using. The two rules you used were the derivative of a bunch of things added together is the derivatives added together. Which some people like to point out is, right, the derivative of, say, like f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. No one ever actually explicitly uses that rule. You just use it because it works nicely and you're like, well, yeah, of course. Also, it doesn't matter if it's addition or subtraction. If you want to take the derivative of two functions subtracted together, you take each derivative and you subtract the results. Similarly, you all just use the constant multiple rule without even thinking about it. The derivative of a constant times your function is equal to the constant times the derivative of the function. You all did that right here, right? The derivative of 5x to the 7th, I'll just point out, the derivative of 5x to the 7th, even though we all just brought the 7 down and multiplied by the 5, what we're actually doing without thinking about doing it is saying, oh, I really have 5 times the derivative of x to the 7th. And then the derivative of x to the 7th is 7x to the 5th, 6th. Sorry about that. And then 5 times 7 is 35. You don't need to show these steps. You're already doing them in your head, but just be aware that these rules are at play. So that we do, because we do use these constant multiple rules often. We're like, oh yeah, the derivative of a constant times a function. I like to say the constant hangs out, and we take the derivative of the function and then multiply it all together. It's more, it's more useful, or it's more kind of explicitly observed if I said, I want to find the derivative of x squared plus x divided by 4. I don't want to, nor do I need to use the quotient rule here. Because what I really have, dividing by a constant is the same as multiplying by a constant. We're just multiplying by the reciprocal of 4. So x squared plus x over 4 is the same as the derivative of 1/4 times x squared plus x. That 1/4 hangs out. And the derivative of x squared plus x is 2x plus 1. If you really wanted to, you could rewrite it as 2x plus 1 divided by 4. Although I probably wouldn't. So whether you're multiplying by a constant or dividing by a constant, that constant just hangs out. Kind of nice. Let's see, what else to say? Oh yeah, let's do that. On the other hand, if someone gave us something like g of x equal to 10x cubed plus 6x plus 5 over 5, I don't know 5, let's 5 is fine, sure. Over 2x squared. I don't want to use a more complicated rule unless I have to. I don't need to use the quotient rule here because I can divide each term by the single thing that's in the denominator. If my denominator was more complicated, like if it was 2x squared plus 1, then I would probably need to use the quotient. But if it's just one thing, we can totally rewrite this as 10x cubed divided by 2x squared plus 6x divided by 2x squared plus 5 divided by 2x squared. And then rewrite that as 5x plus 3x to the negative first plus 5 halves x to the negative second. And then we can just throw the power rule at it. G prime is going to be, for some reason, people get thrown off by a constant times x. What's the derivative of x? 1. What's the derivative of the constant times x? The constant. So it's going to be 5 times 1 plus, I should have written minus, but too late. 3 times negative 1 is negative 3 x to the negative second. And then finally over here, plus 5 halves times negative 2 x to the negative 2 minus 1 is negative 3. I would simplify this just a tiny bit. I'd write it as 5 minus 3x to the negative 2 minus 5/2 times 2 is 5 x to the negative third. Or if you want, you can bring those down to denominators so that you have positive powers. But that's how I would probably choose to write that. Interesting. Okay. Yeah, let's go ahead and. What time is it? Feel like, sure. Like we're kind of rushing things, but sometimes it's good to see all the things. So let's talk about the other rules that are coming your way because, right, again, you're going to have class or have already come your way. You have class on Friday and Monday. I'll see you again on Tuesday. We probably need to talk about the other ones. So let's talk about the product rule and the quotient rule. Yeah, product and quotient. So the product rule. For the product rule to really be, what's the word I'm looking for? To really kind of make sense, I think, to have an example that's worthy of the product rule, we need a couple other things. So let's briefly talk about the derivative of sine and cosine. So what is the derivative of f of x equal to sine of x? There's a couple nice ways of thinking about this. One way is graphically. So I graph sine of x, or at least one period of sine of x, has the point 0, 0, pi over 2 comma 1, pi comma 0, 3 pi over 2 comma negative 1, 2 pi. Looks kind of like this. And now what we're going to do is we're going to graph the derivative by graphing the slopes of the tangent lines. So, try and line things up here. Over here at pi over 2, what's the slope of the tangent line? Definitely. And over here at 3 pi over 2, the slope of the tangent line is also 0. Now, it's a little bit harder to know exactly what the right value is. But at the origin here, slope of the tangent line looks like it might be, well, it's certainly positive. And that tangent line looks like it could be the line y equals x. And it actually is. That slope is positive 1. Similarly, right here, this tangent line that actually goes through the graph, which is kind of funky, has a slope of negative 1. And back at 2 pi, we're back to having a slope of positive 1. And then if we graph this graph, what does it look like? It does. Here it is cosine. And then we could do the same thing to find the next derivative, and the derivative of cosine would be negative sine. Alternatively, you can use the limit definition. If you want to find f prime of x, it's the limit as h goes to 0 of f of x plus h minus f of x, all of h, which is the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Ooh, now what? Now we have to use the angle sum formula for sine. So just as a reminder, because I imagine you may have seen this before, but it probably doesn't stick out in your memory. Sine of a plus b is sine a cosine b plus cosine a sine b. And cosine, just to be complete, of a plus b is cosine a cosine b minus sine a sine b. And then if you ever need the angle difference formula, you just change the signs. Cool. But what that means for us here is we can rewrite this as the limit as h goes to 0. It's going to be a little bit messy. So x is our a, h is our b. It's going to be sine of x cosine of h plus cosine of x sine of h minus sine of x all over h. Okay, watch for a second while we break this up. I'm going to break this up as two fractions. The first fraction is going to have the sine of x times cosine of h minus the sine of x all over h. And the next fraction is going to have the cosine of x times sine of h all over h. And now I'm going to look at the important parts. So I'm going to rewrite this as the limit as h goes to 0 of, I'm going to factor out the sine x from this first fraction. And I'm left with cosine h minus 1 all over h. Plus the limit as h goes to 0. I'm going to factor out the cosine x here to have sine of h over h times cosine of x. All right, now I know it's been a little while. As h goes to 0, what's the limit of sine of h over h? It's 1. So this part here is going to be 1 times cosine of x. X has nothing to do with h, so we don't even care about the cosine of x there. It's just like doing its own thing. Over here, and this one's probably less memorable, the limit as h goes to 0 of cosine h minus 1 over h, I will tell you it is 0. We did it before. It's been a little while though. The way you would do this is by multiplying the top and bottom by the conjugate. Cosine h plus 1, you get a 1 minus cosine squared, or cosine squared minus 1, which becomes negative sine squared on top, and it works out. But I don't want to spend too much time about this. So look, we get sine of x times 0 plus 1 times cosine of x, which is cosine of x, which is what we said the derivative was. How lovely. So the derivative of sine is cosine. The derivative of cosine is sine. So those are your first two trig derivatives. Derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. But now I want to ask the question, if f of x is equal to x cubed times sine of x, what's the derivative equal to? Well, let me tell you what it's not equal to. The derivative is not 3x squared times cosine of x. We cannot take the derivatives of each factor and just multiply them together. Let me show you an example that you believe more. Let's say our function is an unsimplified x to the third times x to the fourth. The derivative of x to the seventh is 7x to the sixth. And I will point out that if I take the derivative of each part here and said it was 3x squared times 4x cubed, which is equal to 12x to the fifth, those are not the same. So I really want to emphasize, we cannot take the derivative of each product and or each factor and multiply the results together. It doesn't work. So what we need to do this is the product rule. Here's what the product rule is. The product rule says that the derivative of the product of f of x times g of x is equal to f prime of x times g of x plus f of x g prime of x. Or as I like to think of it, the derivative of one piece times the not derivative of the other piece plus the not derivative of the other piece times the derivative of the first piece, or whatever, whichever way you want to say it. Like one derivative, one not derivative, and you want to make sure you get each function's derivative showing up once. It also can be extended to products of more than two things. So just as a quick extension here, the derivative of f times g times h, you're going to get three things added together. Each derivative has to show up once. It'd be f prime times g times h plus f times g prime times h plus f times g times h prime. And you can do this for any number of things, 4 things, 5 things, 6 things, whatever. You always get that many things added together, and each derivative has to show up once, multiplied by all the other not derivatives. So let's see if the product rule actually works for the function that we just said we already know. So if I want to say that my function is x cubed times x to the fourth, then using the product rule, my derivative should be the derivative of the first part times the not derivative of the second part plus the not derivative of the first part times the derivative of the second part. And if I simplify that, I get 3 times x to the sixth plus 4 times x to the sixth, which is 7 times x to the sixth, which is what it should be. So it looks like the product rule does indeed actually work. It's great because it should, because it's the product rule. But that means we can also then use it for things that are not just something we can simplify. If our function is x cubed times sine of x, then the derivative is going to be the derivative of x cubed times the not derivative of sine plus the not derivative of x cubed times the derivative of sine. And that's it. That's as simple as it gets, really. You could arguably factor out an x squared. There's no value there. There's minimal value there. The value there is if you're trying to later on find critical points of this function, which we find by setting the derivative equal to 0, then factoring is a value add because then you can get your answers. But typically, you would not simplify this any further. You would leave it as is. So, what time is it? Okay. Why don't you all find the following? Find the derivative of x to the 8th times cosine of x. Bless them. And has anyone talked about the derivative of e to the x yet? It is itself, but has anyone instructor talked about it yet? Okay, good. Some people do it out of order, kind of, which I find weird, but sometimes they do it like I've done here to talk about product rule things. So here for the derivative of x to the 8th times cosine of x, it's going to be, sometimes people do this instead of actually writing it out, they take an extra step and they say it's going to be x to the 8th prime times cosine of x plus x to the 8th times cosine of x prime. If they feel like maybe it's just like they just want to think about the rule and didn't want to think about what these derivatives actually were. And sometimes they're more complicated and the chain rule starts becoming a thing. But then we say, okay, that's going to be 8x to the 7th times cosine of x. And looking ahead, before I write this plus sign, I know the derivative of a cosine is going to be negative sine. So instead of writing plus x to the 8th times negative sine of x, I would rather write minus x to the 8th times sine of x. Cool. Yeah, there's so many rules. Yeah, let's give ourselves the quotient rule too. Here comes the quotient rule. The quotient rule is almost the same, I think. Here's what I mean. So here's the product rule. Again, it says the derivative of f times g. When I write f times g, I mean f of x times g of x. We just don't always write that. It's going to be f prime of x times g plus f of x times g prime of x. I'm not writing the x's, I am saying the x's. On the other hand, the quotient rule looks almost the same. Here's what I mean by that. The derivative of f divided by g, the numerator is almost the same as the product rule. It's going to be the derivative of f times g minus f times the derivative of g. But then we have to divide by the denominator squared. People have different ways of remembering this. Some people like to say low d high minus high d low all over low squared. I literally say all the words in my head. I say it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. That's just what I say in my head. You should say whatever works in your head for you. Yeah, so quotient rule. Now we can look at things like the derivative of x cubed plus 5 over x squared plus 9. And then you throw the quotient rule at it. So it's going to be, okay, so it's the bottom times the derivative of the top minus the top times the derivative of the bottom. That looks terrible. I should not write parentheses there. If I don't write the parentheses there, it looks like it's a minus x cubed plus 5 times 2x. I need it to be minus all of x cubed plus 5 multiplied by 2x, all divided by the denominator squared. I would not simplify this unless I was asked to or had a good reason to. You could though, right? You could multiply at the top and get 3x to the fourth plus 27x squared minus 2x to the fourth minus 10x all over x squared plus 9 squared. And then you can cancel some stuff and get x to the fourth plus 27x squared minus 10x all divided by x squared plus 9 squared. I don't see much value there. Other than if I was trying to set this equal to 0 and solve, then I would want to do that simplification. Sure. What about the derivative of, we might as well go there. What about the derivative of sine of x divided by cosine of x? Quotient rule. It's the bottom times the derivative of the top minus. So notice I write this kind of out of order, right? The rule is actually written as f prime g minus f g prime. I'm usually actually writing it as g f prime. That's totally fine. You can always change the order of multiplication. You can't change the order of subtraction, right? You definitely need to make sure it's the bottom times the derivative of the top first minus the top times the derivative of the bottom second. That's why I'm writing these this way. That's why I'm writing primes instead of actually writing the derivatives. Because if I just wrote the derivatives, it would be cosine times cosine minus sine times negative. And it wouldn't be exactly clear which one was the bottom, which one was the derivative of the top, or vice versa. But now let's make it clear. This is going to equal cosine of x times cosine of x minus sine of x times negative sine of x all over cosine squared of x. And then you might observe that on top we have cosine squared x minus sine is plus sine squared x. And what's cosine squared x plus sine squared x? Show me on your fingers. Yeah, trig identity. Cosine squared of an angle plus sine squared of the same angle is always equal to 1. Unit circle. So that's equal to 1 over cosine squared of x. Or in a less sine and cosine kind of way, the derivative of tangent of x is equal to secant squared of x. And yeah, we'll do one more. So I'll point out that we can find the derivatives. We will. Let's do all of them. They're not that hard. We have a good 4 minutes. Sure. Let's do the derivative of cotangent next. That's going to be the derivative of cosine of x divided by sine of x. I will just say next week we will practice this more, but I figured I might as well show you the trig derivatives because they're there. But definitely you want to spend time making sure the power rule, the product rule, and the quotient rule you need to practice it, right? Like you've seen it a couple times, have an idea of how it works, but making sure you actually practice it so you remember that it's f prime times g plus f times g prime, or f prime times g minus f times g prime over g squared, and just doing it like a bunch of times. In fact, I believe on Canvas there is a handout with like most of there's a handout that has a lot of derivatives, but I think a lot of them require the chain rule. So you have a book. There's lots of problems in the book. Use the book. Do lots of problems. Of course, do the homework. And so let's see, here we have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Now we have negative sine squared x minus cosine squared x over sine squared x. But negative sine squared minus cosine squared is equal to negative sine squared x plus cosine squared x, which is equal to -1 over sine squared, which is equal to negative cosecant squared of x. Something I've noticed over the years is basically every trig derivative, you can take the version that doesn't have cofunctions and turn each function into its cofunction. The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared with a negative in front. The same thing works for the last two here. Derivative of secant of x is the derivative of 1 over cosine of x. Using the quotient rule, that's going to be the bottom times the derivative of the top. Derivative of 1 is 0 minus the top times the derivative of the bottom, which is negative sine, all over the bottom squared, which you could write as positive sine of x divided by cosine squared of x. Nobody writes it that way. Instead, we rewrite it as 1 over cosine x times sine x over cosine x, which we then rewrite as 1 over cosine is secant of x, sine x over cosine x is tangent of x. So the derivative of secant of x is secant of x times tangent of x. And I will leave it to you to prove on your own, which you should really do, with the derivative of cosecant of x, while using the same idea I said before. If the derivative of secant of x is secant of x times tangent of x, then the derivative of cosecant of x should be I know you know what I want. Instead of secant, I should have cosecant of x times cotangent of x. I know it, you just don't want to say anything. So it's going to be cosecant of x times cotangent of x, and then there's a minus sign in front. But look at the pattern, right? Derivative of tangent is secant squared. Derivative of cotangent is cosecant squared with a minus sign. Derivative of secant is secant tangent. Derivative of cosecant is cosecant cotangent with a minus sign. Also, notably, every cofunction, cosine, cosecant, cotangent, has a negative derivative. And the other three, sine, tangent, and secant, have positive derivatives. There's nice patterns to be aware of. You don't have to remember quite as much as you might. Meaning, like, you can memorize less things if you recognize the patterns. All right, that's all I have to say for today. I mean, I could say a lot more things, but time is up. So that's all I will say for today. Tuesday, we'll probably talk about the chain rule and more of the quotient and the product rule.